Hello and welcome to this video. In this video we're going to be looking at the energy stored in a capacitor. So if we're going to go back to our electricity knowledge, we then know that we're going to have energy transfers in any electrical component, right? Unless it's something like a voltmeter or a ammeter. We have to end up with some sort of energy transfer. In a resistor, the energy transfer is to any waste energies because it's just trying to get rid of some of that energy. In a light bulb or a lamp, it's just light energy. And in capacitors, our goal is not to transfer energy but to store it. We're trying to hold that charge so that we can then transfer it once we've switched the position so that it can discharge across a separate component. And we need to then be able to come up with some sort of expression to how would we actually be able to get the energy stored. How can we calculate the energy stored between two capacitor plates? So first we need to figure out a way to just investigate capacitors. We need some sort of way that we could measure the capacitance first. And in that way we can then say, we can probably assume that the amount of energy that a capacitor can store on it is going to be proportional to the capacitance in some way. So what we can say is we know the equation that C is equal to Q over V. Okay, we said this is the definition of capacitance. And so what we can say is capacitance from this equation must be a constant for each capacitor, because I could rearrange this as Q is equal to C times V, and I end up, if I wanted to plot this graphically, with Y equals mx. So I end up with an ability to say that the capacitance is just going to be the gradient of a QV graph. So if I were to then say, let's take a measurement of the charge held on a capacitor plate, and then we look at the charge held and the volt. So this charge held is in coulombs and this potential across it is in volts. And I want to see the kind of relationship where if I increase the potential that I have across it, how does the maximum charge that I can hold across it increase? And we know from this idea here that it has to be linear, right? So we get this graph here that is a linear graph where the gradient of this, the gradient M, is the capacitance. Okay, so we get the gradient of a QV graph is capacitance. But then the gradient isn't the only thing we can calculate. We can also calculate the area underneath it. So then we have to think, is there any use to a Q times V? Okay, what would that actually give us? So we then say, what is QV? What kind of measurement is that? And the way we can figure out what kind of measurement we're making is to look at the units of it. Now, if we find the units and then we get a units of distance, we know this is a unit of distance, and we have to figure out what kind of physical meaning that has. So if we were to say we have an equation that is QV, now we would say that Q is just a measure of charge. Okay, so Q is measured in coulombs. And we know voltage, or potential difference, we had a definition for, which was the work done per unit charge. So the voltage is measured in joules per coulomb, if you wanted to go into a different SI unit. And then actually this charge, or these coulombs, will cancel each other. Okay, and so actually QV is an amount of energy. Okay, and that means that the area underneath here must be the energy stored. Okay, so we get that Q times V is the energy stored, but this area here is actually a triangle. So now we can formulate an expression for the energy stored to be, so the energy stored is, we're going to call it E, is actually going to be Q times V divided by 2. So that's a half times the base, which was V, times the height, which is Q. Okay, so this is your first equation for the energy stored by a capacitor. But the problem with this is we could then have difficulty understanding how the relationship between the energy stored and the charge and the voltage is going to change. For example, if I say I'm going to increase the potential across this capacitor, what happens to the energy? You would initially assume that this is going to obviously increase. But then by what factor? Because if I increase the potential, I'm also increasing the charge because I have this direct proportionality here. So then we need to think about how can we get it so that we can just look at how the potential affects the energy and just look at how the charge affects the energy. And we know that a relationship between Q and V is that Q is equal to C times V. So then we have to say C is a constant, right? We know the gradient of this is constant because it gives us a straight line, which therefore must mean that if I can explain E in terms of C and then a different component or potential or charge, then I should end up being able to explain the proportionality between them. And so I can say, if I just want to get it in terms of V, I can substitute the fact that Q is actually equal to CV from up here, from earlier. And that leaves me with the fact that I have a half that stays the same, and I have a C, and I have this V times this V, so I have a half CV squared. Now I can say for certain that if I increase the potential, I'm actually increasing, so if I double the potential, for example, I'm increasing the energy by a factor of 4. Because my proportionality is that E is proportional to V squared, since half C is always going to be a constant. Then the last thing we can say is, what if I wanted to look at the charge instead, and I would actually instead have to sub V is equal to Q over C. And when I do that, I end up with the same half at the start, but now Q stays the same, but I'm now going to times it by this Q, so I get a half Q squared over C, and actually it shows that I have the same sort of proportionality with the charge as well. If I double the charge, I end up increasing the energy by a factor of 4. And the only difference between these two is the fact that you have C over 2 as the constant in this equation, and you have 1 over 2C as the constant in this equation. But if the capacitance is always constant, it doesn't really matter, because usually when they ask these questions, they'll either just give you the capacitance and ask you to calculate the energy stored, or they will give you an initial charge and they'll say, what happens if you double this? How does the energy stored change? So this then gives us all of our expressions for the energy stored on a capacitor. And this is how we calculate that. So you can always get two things from a QV graph. You can get the gradient being the capacitance, and you can get the area underneath being the energy stored. And then we've investigated each of the proportionalities between the energy stored and the charge changing and the potential changing.